I'm actually president of the Planetary Science section, but never mind. It is my great pleasure to introduce as our plenary speaker Dr. Jim Green, the NASA chief scientist, who is going to tell us about the exploration, future exploration of the Moon and Mars. Jim?
Thank you very much, Rosalie. Well, it's really a great pleasure to come and talk about what NASA's view is of the future lunar and Mars exploration, as we also connect with much more of our commercial partners now that they're coming along and demonstrating a significant capability, and continue on with our international partners. So let me first start with the fabulous year that we've had. This is the 50th anniversary, of course, of Apollo 11. Our astronauts were the first to step foot on the moon, and they immediately got busy doing a variety of science. It turns out Neil Armstrong had already put down on the surface an experiment, and here is Buzz has just completed putting what is a seismic instrument down on the surface. But the experiment that Neil first put down on the moon was this retroreflector. And in this retroreflector, we're able to, it's a passive instrument, of course, we're able to fire lasers to this reflector, obtain that information, and then through time delay, determine the distance to the moon. And we've been doing it every year for 50 years, you know, as if we don't get it right. But it's changing, so that makes it a fascinating experiment, of course. Here's a quick summary of the Apollo Lunar Exploration Program. Of course, these are the 6 missions that landed on the moon, and as you can see, they're all on the near side. In addition to that, they're close to lower latitudes. They're not at high latitudes. And they brought back a significant amount of lunar material. So that's rocks and regolith and cores. And in fact, we're in the process this year of opening some cores that we've never opened before. So we're really pretty excited about that. So what were some of the things that really came out of the Apollo program? What did the samples, this 850 pounds worth of material, tell us? Well, it tells us that the moon is old, okay? So the rocks here on Earth, because of our plate tectonics weathering, our oceans, the things that go on in terms of modifying the geological processes on the surface, you know, the oldest rocks are in Australia or in Greenland, and they're 3.6 to 3.8 billion years old, okay? And so material from the moon that's at 4.5 or so billion years is really significant, because it tells us then, of course, that the Earth and the moon as a system is indeed that old. We also found through certain materials, the anorthosite that they brought back, that the moon, as it accreted quickly, had a complete molten rock surface, a magma ocean, we call it. And then that cooled. And then what happened over time is the major geological process on the moon, which is impacts, you know, and so the entire impact history of this inner part of the solar system, Earth, Moon, and of course that would be Venus, Mars, Mercury, is really on the surface of the moon for us to be able to tease out and go back. And so when the rocks came back and we started dating them, we really got quite an important array of material and dating because of these impacts are telling us, creating the new rock material and dating it and giving us that history. And indeed, there was quite a bit of volcanic activity. The Mare that we see on the near side of the moon every night that you go out, that you can actually see, particularly during full moon, is really molten material from lower crust that is filled in impact basins, huge impact basins. And so that molten material, after the moon had cooled and in many hundreds of millions of years after the moon was actually formed, gives us an important understanding of how these geological bodies, and the moon in particular, evolve over time. The isotopic analysis from the material we brought back clearly indicates that it's much more Earth-like. So when we put this information together, we can learn a lot about the Earth-Moon origin. And one of the first things that we were able to do, because of the way the moon was formed, its impact history, it tells us that when we look at regions where there's a lot of impacts, that's older than some of the newer regions, where, as I mentioned, lava flowed in, you got a subsequent set of impacts, and so that's a newer region. And because we have that material, can date it, we can actually get a chronometer of that history that we use at a variety of places, such as Mercury and Mars, and even many of the moons of the outer solar system. But it's tantalizingly incomplete. And so returning to the moon is really important because we want to be able to get a significant number of material from different regions and date that and really do a better job of creating that chronometer. And of course, the reason why is it's going to tell us a lot more about what happened in the evolution of the Earth. Now, after the Apollos, there was kind of a dearth of lunar measuring systems and orbiters and landers, and it really got going in about 1990. And then there was really quite a history of these missions. Here's a little graphic that shows when they were launched and then how long they lasted over a period of time. And this rebirth of examining the moon from orbit in particular, and a few of the landers that have occurred, really gave us an enhanced view and a huge set of knowledge that we then can combine with the Apollo measurements to really understand the moon much better. So let me go through some of those observations. Here, of course, is the moon, the near side and the far side. The moon is tidally locked. Those Mare areas, as I mentioned, are basaltic material, lava flows that have come into huge impacts that occurred in the lunar history. This also is where a lot of the mass is concentrated because the Mare has some of the iron and higher Z materials that are in it. We can get from altimeter measurements, the altitude of the moon, and we can see the highs and the lows in this colored version where the blues and the purples are the lows and the reds and the whites are the very high. We see that the far side has both the lowest and the highest areas, and in fact it's about 14 kilometers in distance. And one particular area that's really exciting is this called the South Pole Aitken Basin. We can recognize that this must have been an early impact. Now, lunar magma didn't flow in and create a new Mare here. All right, so we have to consider what happened and why that didn't occur in the lunar evolution and its history. But this impact, this old impact, is so huge, and it blew away a significant amount of crust. This is a very, very exciting area to go back to on the moon because we want to look at the lunar rocks here. Could be lower crust or upper mantle material. Now, we can't even get to the mantle of our Earth, and maybe we have opportunities to really study what mantle material is like under those huge pressures and temperatures as terrestrial planets come together. Also, we see these highs, the far side, when we look at it, and in this view, tells us the crust thickness. And the crust on the far side is thicker by several tens of, maybe even as much as 30 kilometers thicker on that far side than it is on the near side. So we have to put all that information together to be able to really understand the history. So I'll give you a little overview as to what we think has happened over time with the Earth-Moon system based on all these observations from the Apollos, all the observations from the orbiters and this renewed interest in the 90s and into the 2000s. All right, so clearly it starts out as our sun is created and the solar system is starting to come together, that two bodies, we believe, that were formed in about the same region of space, a proto-Earth and another large object, probably the size of Mars. That's what the models seem to indicate. It has to be a rather large object, collided early on in the formation process. Now, we can actually model what happens in an example like this. So here's the proto-Earth in this artistic view, and the object we call Theia, fondly called Theia, hitting each other, and then we now can model that. Our computers are good enough that we can break that up, and on the right-hand side you see indeed what the computers can actually begin to do the analysis for. And so here's a little simulation. The Theia slams into the proto-Earth. The core of Theia, which may be fairly significant at the time, re-enters the Earth, which then also gives us the indication that maybe the moon doesn't have as large a core, and this is true based on seismic and other observations. And then the moon will form out of the debris that occurs. So where is the moon going to form in this particular example? Well, it has to form beyond a certain limit, a certain region. It's called the Roche limit. So anything inside the Roche limit really can't form another body. Gravitational interactions with the larger body, Earth in this case, the proto-Earth, is going to keep them apart. So that means then, as material begins to accrete beyond that, we actually are going to end up with the body that we call the moon. So then that means the moon actually formed just outside the Roche limit, fairly close to the Earth. And then clearly over time it has to move away from the Earth. And this is where also the Apollo observations come in handy with the laser ranging, and I'll talk a little more about that. So here's our initial conditions where the moon is formed just outside the Roche limit at about 3 Earth radii. And then the proto-Earth is becoming the Earth as it begins to cool. And of course, the conservation of angular momentum says it has to be really spinning. So it's about a 5-hour day on Earth. And so the moon is huge. In comparison today, where you see the lookout and you see the moon, where the moon formed just outside the Roche limit is on the order of 16 times larger. So you can imagine how it dominates the sky. And of course, what we found by laser ranging is indeed that the moon is moving away from the Earth, all right, about 1.5 inches a year, all right? And right now it's at 60 Earth radii, all right? So it really has changed the dynamics, and the important aspect of the Earth-Moon system is that the moon has done a great job enabling the Earth's axis to be retained at a fairly constant angle with respect to the ecliptic for billions of years, and that has helped our climate not be so radical. When we look at Mars and in particular, we can see how radical the climate has changed over its time because the axis is not stable as it is here on Earth. So now what we have to do is try to tease apart some of the ideas of how come the Farside is thicker in terms of the crust size. And of course, here is now the moon forming in this particular area. One particular theory is perhaps there's another object forming outside the Roche limit of fairly significant size, and that object then indeed accretes with the moon, causing that thicker crust. So that's one of the major theories. We're not quite sure how that's going to go. We have to tease that out by bringing more samples back from the moon, particularly on that far side, which has been largely unexplored, in particular from the surface, other than the recent Chinese mission, which has landed in the South Pole Lake and Basin. Another theory is that indeed as the Earth was cooling in an extremely hot environment and the moon was coming together just outside the Roche limit, that the extreme heat was literally vaporizing aspects of the moon that was pointing towards the Earth, and that material then falls on that far side, creating the thicker crust. And so we believe we can differentiate that by bringing back the right samples and understanding them. Well, here is the moon in a false color infrared light that tells us how exciting in terms of the mineralogy of the moon that's laying on the surface because of the different types of impactors that occurred over the billions of years of the lunar history. So also from these kind of observations, it gives us a greater hint as to areas on the moon, both in the near side and the far side, that we want to be able to collect material and bring that back and analyze it, because that material has its origin elsewhere in the solar system before the impact. Now, the bombardment history, as I mentioned, is what we're trying to put together. And in this particular case, when we look at these basins, these are large impact regions, and we have a notional idea as to how they are, their date, because we brought back the rocks and we can date them. We recognize that there's an extreme variation. There's a time period of after the moon came together of intensive bombardment, then there was a lull, and then perhaps another bombardment occurred. In that bombardment, between 4 and 3.8 billion years ago, we call the late heavy bombardment. All right, and so we've known scientifically about the variation in these ages of the bombardment history of the moon for quite some time. And it's only been in about the last 10 years or so that we really started to figure out what some of the origins of this massive bombardment that happened 400, 500, 600 million years after the moon was created. And it really begins by trying to understand how the solar system was created. As I mentioned, our computer technologies were getting so good that indeed we can model the Earth-Moon impacts and creations. And so that's been extended now to the solar system. Many of the modelers in the early 2000s would take those codes and try to create a solar system. And in this particular example, they were trying to form planets. Our solar system, you know, Jupiter, Saturn, Uranus, Neptune, and more of the Kuiper Belt and debris fields left over from this formation as they exist today. And what they were finding as they run their codes for billions of years, they can't create, in particular, these outer planets, in particular Saturn on out. And so in Nice, France, a number of scientists were tackling this particular problem. And there was Hal Levinson from the United States there. And they were commiserating over, well, what do we need to do? What's wrong with our codes? What physics are we missing? And in fact, the idea came up is, well, let's just figure out how to create these planets, how we can get, 8 or 9 planets formed in a solar system that have approximately these sizes. And then another scientist said, well, the only way to do that is you bring them in. You start with the seed that's closer so that they can accrete quickly. Because indeed our solar system, within 10 million years or so, was accreted and put together. And so that basic principle, begin that formation closer to the sun, and then running the codes, indeed enabled them to create what were solar system-like planets, but not in the positions that the planets we have in our solar system are today. So this was really exciting, but a nice thing occurred in running the codes, since they were already set up to run for billions of years. There's interactions, gravitational interactions that are going on between these sets of planets in those positions closer to the sun. Now here's a simulation. We're going to look down on the solar system, and you see the orbits, Jupiter, Saturn, Uranus, Neptune, all right? And then you see the Kuiper Belt, the cometary and the icy particles. And you can see they're all formed below 20 astronomical units. As you know, Neptune is out nearly twice that distance from the sun. And so as you run the codes, and this is a frame out of one of the codes at about 850 million years after they're formed, and then we're going to run this, and so look at what happens at about 890 million years. And that is, gravitational resonances interact, throwing the outer planets outward. Jupiter moves a little bit inward. In fact, it's believed Saturn, because of the mass of Saturn, that enabled us to hang on to Jupiter so it doesn't sweep out the inner planets. And we actually end up with a solar system much like the one we have today. But that initiates the entire debris that the smaller bodies that are in this solar system to be able to rain in on the inner planets. And so independently, that occurs at about 3.8 billion years after the initial creation of the solar system at 4.6 billion years. That fits well with our understanding brought back from, and dating of the rocks brought back from the moon and the examination of a time period that we call the late heavy bombardment. So here's a quick summary. 4.2 billion years, all these outer planets were closer to the Earth. Gravitational resonances pushing them out, moving the small bodies, and then over time clearing those out also, as normally done. So this has been really an exciting time for us to really put theory and modeling together. So when we look at the moon, some of these newer observations that are absolutely revolutionary are now at higher latitudes, where we haven't been, where we haven't set foot down on the surface of the moon. Here's the South Pole over a 1-month period, as you can see the variation of the light. And indeed, this is exciting because it tells us that there are regions in the South and North Pole where the craters, as you can see on the left side, are in permanent shadow. And so these are conglomerations of 1-month data where you can get the illumination field, but also with the Lunar Reconnaissance Orbiter, we can understand the temperatures. And as you can see, matching the right side, the temperature distribution, with indeed the permanently shadowed areas, that these are some of the coldest places in the solar system. They're colder than the surface of Pluto. Now, what's happened over time, because of the bombardment history, is, of course, comets have bombarded the inner part of the solar system, bringing water and volatiles. Of course, asteroids, and the more we know about asteroids, the more we recognize the significant amount of water that is also in these asteroids. And so what's happened then over time, looking at another set of measurements from a couple spacecraft, we can actually tease out that the North and South Pole has a significant amount of hydroxyl, OH, and or H2O, and a significant amount, 100 to 200 million tons total between these two hemispheres. We also see the pattern here is shown in what we have measured with the epithermal neutrons, indicates that it's not centered strictly with the polar axis of the moon, and in fact it indicates that the polar axis has changed over time. And that's completely understandable when you think about how the mass distribution of the moon changes, through the volcanic processes that are occurring from these impacts, perhaps potentially from the creation of the Highlands or even the South Pole Lake and Basin. And we have to put that timeline together. We haven't completed that exactly yet, but it's an area of extreme important research. We're finding today that there's still a water cycle going on. Now, when we brought the rocks back from the moon, coming from that primarily low latitude region, they looked really pretty bone dry. We actually have better instruments now. We see, yeah, there is some water there. But what we're finding with the LADEE mission in particular, which was our Lunar Atmosphere and Dust Dynamics Explorer, is that during certain periods of time, clouds of water would appear, and LADEE would fly through those You know, the whole moon would participate in this outgassing of water. As shown in the left side upper panel are these time periods, these bursts of water clouds where Laddie has been making measurements. And it turns out the large one was timed nicely to the Gemini meteor shower. And this really gave away what the process is all about. And we're now able to identify these indeed with the meteor showers that we're getting. So as the meteor showers are occurring here on Earth, they're also, of course, occurring on the moon. The impacts, particularly the really fast one, creates a shock wave moving through the lunar soils. And that releases water. And of course, the cold traps in the northern and southern polar cap region is a primary area of interest for that water to go to. You know, thermodynamics tells us that that will happen. So if the water doesn't get ionized and swept away by the solar wind, it actually has a tendency to move north or south. And then that enhances these polar water regions. So I just talked about a few of the many exciting scientific things that we really want to do on the moon. You know, we want to get a better idea of the chronometer by bringing back more lunar material and dating them. We want to understand more fully this late heavy bombardment and the period of giant planet migration. You know, giant planet migration must be happening with exoplanets because we're seeing large Jupiters on highly elliptical orbits. They couldn't have possibly formed there or close to their parent suns. They must have moved there, and then one of the big reasons that they could do that is through gravitational resonances. So we want to be able to investigate these polar water regions. We need to go to the poles. We need to create cores, bring those back, and really tease out the history of the moon, just as we do the history of the Earth by coring ice in our own polar caps and bringing that material back. We believe that that will tell us a lot about periods of time where comets and asteroids are impacting, periods of time when the late heavy bombardment and the giant planet migration periods. And so the amount of water there is only estimated at the moment. We really need to get some ground truth. There are many other scientific things that we want to do in the moon. For instance, that Farside is in the solar wind all the time, other than when it's in the Earth's magnetotail, but the near side is protecting it from Earth material that flows from the Earth, bombards the moon on the near side. And so as the moon swings around, it's in the solar wind. That far side has the history of the sun buried in its soils that we really want to get access to and understand. We understand space weather and the history of the sun and space weather purposes, and understand, therefore, what the sun might be like in the future. Also, even though we deployed seismic instruments, they had major limitations. You know, we have much better capabilities today to really be able to tease out the size of the crust, the mantle, and the core. We suspect the core is small, as we talked about earlier, because most of that core material went back into the Earth. And then the far side opens up wavelength regimes, particularly in the radio area, where today here on Earth we have a lot of radio interference. We can't make these measurements unless we go to the far side of the moon. And they're extremely important to understand based on even cosmology, understanding the universe. So what's happened also in December 2017 is we got the Space Policy Directive 1. And what this is really all about is really begin the process in an accelerated way, leaving low Earth orbit, moving outward, going to the moon with in a sustainable program, and then on to Mars. And we do that in cooperation with our commercial community that is really coming on strong, along with our international partners. And so the concept of sustainability is also a new one for us. You know, the lunar Apollo missions were sorties. We want to be able to go to the moon for longer periods of time than hours today to weeks to perhaps months in the long run. For longer periods of time requires what we believe is an infrastructure to develop and leverage and utilize over time. Most recently, the administration has challenged NASA to be able to do that, budget permitting, in a way that we can go to the South Pole, that's the targeted area that we want to put humans on, and have the first woman and the next man on the South Pole of the moon by 2024. And NASA, of course, is aggressively working that. Our commercial partners, we've selected quite a few through what we call the Commercial Lunar Payload Services opportunity. Here's a set of 9. We've actually just announced 5 more. And so there's quite a bit of commercial capability we want to be able to leverage. NASA is also investing into a variety of new instruments, developing lunar instruments to be able to go on these systems and land on the moon at a whole variety of locations. So scientifically, we're interested in the whole moon, but indeed, many of these will go to the South Pole and begin the precursor measurements so necessary for us to be able to then be ready for humans to explore that particular area. The ability for us to do this with humans requires a powerful rocket, much like the Saturn V. NASA's developing the Space Launch System, the SLS, also the Orion capsule. These two are coming along, and we'll see in the next year our first launch of this. This is called the Artemis program. So let me review what our plans are for Artemis Phase 1. The target, of course, is to the lunar surface by 2024. While we're working with our commercial and international partners to land in various regions on the moon, as you see here, we'll also have our first Artemis mission. This will be uncrewed. We want to wring out all the problems that you can't always anticipate with systems like this. This Artemis 1 will indeed do like a figure 8 to the moon and return, much like what we did with an earlier Apollo. And then, of course, Artemis 2, after about another year from that, we'll take advantage of what we've learned from Artemis 1 to be able to have a crewed launch to the moon and return. This then enables us with EELVs, other types of launch systems, to begin to develop an infrastructure. This is an element of the sustainability. This is an element of wanting to build a what we call gateway at the moon, a mini space station, if you will, that will be used and built up over time and used to be able to dock and then return to the surface and come back. And so as we build this gateway, the gateway has a number of elements. We're working with our international partners. And in fact, the ESA ministerial just was completed, and ESA has a nice, healthy budget to be able to work and participate with NASA, and we're really happy about that. The orbit of the gateway is a highly elliptical orbit, where the Apolloon, the farthest away from the moon, is over the South Pole. That will be a perfect place for us to be able to use the gateway for communication as a relay of instruments that will land on the far side, and of course also on the South Pole, particularly if we end up in areas on the South Pole that don't have good visibility to the Earth. And then finally, down to the surface in 2024 with our first woman and our next man. Then notionally, phase 2, completing that decade, will be a number of SLS launches, performing a variety of research, not only at the gateway, but from the gateway, doing telerobotics and things that we would anticipate doing also at Mars. In fact, many of the instruments that we want to land in the South Pole region will go onto these permanently shadowed areas. We'll be able, as I say, to core, and we want to be able to get these cores back and examine them. but we also want to be able to determine how much water is there and how we can tease it out and then use it in a sustainable way. Of course, water you can drink, breaking the oxygen and hydrogen apart, you can breathe it, and then you can also create rocket fuel. So the water is a critical element of that. But there will be other volatiles there. There'll be CO2 and CO, and so there'll be perhaps far more oxygen than we currently are estimating from our orbiters of today. So the future of the moon, we believe, is quite bright. We want to continue doing science. We want to go in a sustainable way. That means we have to determine what we need to do to be able to live, and that means living not only off the land by extracting materials like water, as I mentioned, but also in a sustainable way for food. The moon is our first place where we want to live and work on a planetary surface, learn how to do that, because Mars will be that next step. We have opportunities well into the future for mining and fuel depot and other kinds of things that we can do with the moon. So what's happening in the Mars area over this next decade? So we have an aggressive program of more scientific research leading to human exploration of the moon. Now, what's happening on Mars? Well, everyone knows in this room, NASA doesn't do Star Trek. It's not like we go where no human has gone before with humans and walk around on Mars. We still have a lot of robotic science we need to do. What's happening right now is we have quite a fleet of orbiters, international. We have InSight and Curiosity working well on the surface. And in 2020, beginning in the July-August timeframe, that window opens up, and we have now an opportunity for many missions going to Mars. So the highway to Mars this mid-next year will be really exciting. Not only UAE, but China and NASA and ESA have plans to be able to live with a variety of rovers and experiments and perform things on the surface. What we're finding out is tremendously exciting. Here's an example of Curiosity landing in Gale Crater. As we bored down below the surface, the red soils on the surface of Mars, we find gray Mars. This particular stuff has carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. It has nitrates in the soils, and the soils are moist, so it's really exciting for us. It's much more Earth-like. We've determined, of course, Mars was a blue planet in the past and had a significant amount of water, particularly in the northern hemisphere. InSight now is landed and is teasing out, seeing perhaps on the order of 200 seismic events. They're teasing out the important ones and trying to interpret those in terms of their origin and understanding the size of the core, mantle, and crust. It also is a great weather station. You can log on and you can get temperature, pressure, and wind velocities. NASA's next big mission to Mars, the Mars 2020 Rover. We've just completed a naming contest where we've asked the kids in the United States to write up a little paper on what they would like to call this rover and send it in. I think the number is well over 100,000 submissions that we have to paw through to determine that top name, and it's going to take us a little while, but I'm sure before launch we'll have it, and we'll have the kid and the families that made that spectacular name happen for us there at the launch. So this is the start of a larger campaign where Mars 2020 going to Jezero Crater, a fabulous delta where water poured into that ancient ocean, will be coring rock over many different locations. They'll be put in tubes, laid on the surface, and then later picked up and brought to a Mars ascent vehicle, which then the captured material in what we call the Oz, the orbiting sample sphere, will be captured by an ESA spacecraft and then brought back to Earth. and then we'll be able to really look at those samples. You know, the history of Mars is in that geology, is in that rock record. Perhaps we can get lucky and understand how Mars changed over time rapidly from a blue planet to the dry, arid world we see today in that record. Perhaps we'll get lucky and see some indication of past life on Mars. When we look at Earth, there are over 4,700 minerals on this planet, and 300 of them are created because of life. So we have opportunities to really understand that history of Mars, and hopefully we can get lucky and make really some exciting announcements based on those results. In the long term, though, the next step is indeed the start of the planning to go to Mars. Right now, we believe we're going to go to what we call a human exploration zone. This is one particular area. It's about 200 kilometers in size. We want to land in an area. We want to be able to live in another area. We want to be able to get access to resources, you know, using ISRU to be able to get underground, tease out the frozen water, much like we would start that process by practicing it on the moon. There's plenty of frozen water underneath the surface of Mars, and in particular, several areas where the old glaciers on Mars have been retained, even at mid-latitude. So we've got some really exciting sites that we're considering. And then, of course, we want to be able to explore in this area. So we have to have the mobility, the ability to go to various places and be able to get material and really examine it. This is very different than the Martian, where every time you land, they're in different locations. We're going to be in this one location for many decades once we get started to do that. So what we have done is we've started the process to look at potential exploration zones. Since doing this needs to be done carefully because it'll be the place that we'll be at for many decades. That's the current plan. The community has gotten together and really proposed a number of these sites. They've needed additional information, and over the last several years, since we've done the first human exploration workshop, we've acquired and tasked our orbiters to acquire new information, and so more information is coming in that enables our science teams to analyze these places. And soon we'll have another human workshop where we look at these exploration zones and then narrow it down to the top few that we really want to go to until we finally pick one. So in closing, this is a tremendously exciting decade looking forward to scientific exploration of Mars, and a really important step with sample return being the heart of that, and quickly exploring, finishing the initial exploration of the moon, particularly in the South Pole region, understanding that before we then send humans there in this next decade. So I'm delighted everyone is coming along and helping us make this happen. Thank you very much.
Thank you so much, Jim.
Oh, my pleasure.
We do have time for questions. We have Eric running around with a microphone. It's kind of hard to see people with hands up. Yes, one question here. And
you need a microphone?
Yes. Hang on.
Yep.
I got.
There, here we go.
Okay, there we go.
I love the moon too, but my concern is how much would this cost? And I think I recall that the Apollo missions cost in 1963 $20 to $30 billion. And a first-class sample was 3 cents then. Now it's more than 50 cents.
Yeah, so NASA's really taken a good look at what it needs to start this process of rapidly going to the moon by 2024. We did a supplemental request to Congress through the administration in this fiscal year. And so those appropriations are being hotly debated and discussed. That may have come to a conclusion as the NASA bill is getting to the point where it may be passed after the end of the continuing resolution on December 20th. So that will be what we need for 2020, okay, which we're in today. In February, we're giving the administration's budget to Congress that does indeed the cost profile necessary to allow us to land on the moon in 2024 with the first woman and the next man. So that budget's embargoed, but it will be released to the public when we submit it to Congress in February. Okay, so he wants to know the number. That's embargoed. Okay, which means even if I knew it, I can't tell you. Or I'll no longer be the chief scientist at NASA, and I don't want to do that. I like what I'm doing.
Other questions? Yeah, we got time for questions.
Jim's got one.
So Jim, this is great for planetary sciences in the planetary sciences section, but of course there's lots of things to do with astronomy, et cetera. Can you say a few words about what we can do from the far side of the moon in terms of astronomy?
So it turns out there's a certain period of time in cosmology that we don't have access to. And of course, wavelengths that we receive over time change. And so therefore in the radio area, in particular in the area of a couple hundred megahertz, which right now is quite cluttered here on the Earth, we can't see into the universe those measurements, and therefore that time that occurred in the past. We can on the far side. On the far side of the moon, we won't have the radio interference, and so actually there's quite a bit of discussion about creating arrays and really looking in this wavelength regime for cosmological purposes and understanding a certain period of time in the evolution of the universe. So from an astronomical point of view, there's quite a number of people that are very excited about that. Now, that's also being discussed, of course, in the astrophysics decadal, which is currently going on, and the importance that has with the rest of the field. And so those are hotly discussed. Relative to planetary science, you know, planetary science does a lot, not just with the moon and Mars, but many other locations and outer planets and Mercury and Venus also. And so we're coming to the point where we're going to start the process of call for white papers and then begin to put the committees together for planetary and then indeed start that program. If you want to learn more about that, over the noon hour today at 12:30, there's a town hall where we are working with the Academy, and we're going to talk about the next series of steps to complete the panels and start the process of the next planetary decadal for the next 10 years. So that's going to be real important.
Mr. Green, we have a question through our Q&A app.
Uh-huh.
Has the lunar landing anniversary reinvigorated the public's interest in space exploration?
I think so. You know, as I look out into the audience, I see a number of people that actually watched that lunar landing and got excited and were inspired. Many of us understand what happens when you really see humans walking on the surface of the moon. You know, and that is a seminal period in history of our past. And we're going to have the opportunity to give this next generation that has never seen these things to really understand what that's like and experience it. And it's going to be even more exciting for those of us that had seen the original Apollo landings and walking on the moon, because being in the southern hemisphere, in the South Pole, it's going to look really eerie. We're going to have long shadows. It's not going to be like one of the images I showed with Neil and Buzz on the surface, where the sun is nearly overhead. And so that's going to be really quite exciting. So indeed, NASA had quite an opportunity to celebrate the 50th. Many different documentaries were produced by many different channels. Many of them were quite popular, and so I think the anticipation is rising. But we'll really, really get it going when we step on the surface of the moon. And then Mars. Yes, that's right.
We have another question through the app. When will the astronaut selection process begin? And what will you be looking for? And will you consider a 65-year-old voice of God?
Okay, so I'm not in the selection process, but I'm delighted to speculate, all right? So let me speculate, and I'll just say it that way. I believe that the people that are going to walk on the moon first are working in the agency today, all right? They're already being trained as astronauts, all right? So soon, and I don't know when soon is, but we will be moving towards announcing who those individuals are, both the primary team, but also the backup team. You know, you have to select, over-select in that area, and then train them. You know, we're talking now about the kind of things that we want to train our astronauts, the kind of experiments that we want to do when humans land, deploy those, be able to acquire samples, be able to bring back material. You know, if we don't bring back samples from the moon, I'm going to say something heretical perhaps, they shouldn't come back. So, I mean, you know, the value of those samples are so important, and in particular, the coring. We can send things into these permanently shadowed areas and get a better indication of how much water is there. As I mentioned, our current estimates from orbit, using some of these experiments that are looking at cosmic ray interactions of underneath the surface and creating these epithermal neutrons as indicators of hydroxyl or water, and water, H2O, our current estimates is between 100 and 200 million tons of water, all right? Well, there may be more, okay? There may be more. We really need that ground truth. And so it's going to be an exciting time.
Well, are there some plans to put again seismometers on the moon? Well, we have one seismometer on Mars that will help for the moon to get maybe the depth of the interface between the core and the mantle, and a better idea of the bulk composition of the moon.
Yes. So indeed, even though we deployed on several of the Apollos, not all of the Apollos, seismic instruments, they were had many limitations. Okay, so they had many limitations in terms of the resolution. Also, we found out something surprising to us, and that is the crust rings. Well, that's part of the geological process of the moon, the impacting that's been going on, tearing up the surface where those impacts are, the top geological process, making that material such that it supports seismic waves and directs them that way. And so there's only some new papers that have come out that have really teased out much more of those signals that we actually received that go well beyond the crust and into the mantle and perhaps touching the core. So we need to do a better job. We need to do a much better job. In the last planetary decadal, seismic stations, several on the surface of the moon was one of the primary objectives. In this last decade, we were not able to be able to select a proposal and a team to move forward to do that. But I think when we look at what we want to do on the moon, it's going to now be more likely in this next decade we'll accomplish that.
We have time for one last question from the app. In working with the commercial partners, will the data collected be public, or will there be restrictions?
Really good question. I asked several people, in fact, Steve Squires in particular. Steve is the project scientist for Blue Origin. You know, that exact question. And it's certainly clear at this point that NASA instruments that will be taken to the moon acquiring data will fall under NASA rules in terms of being able to have the data open and available. Other instrument data, it's not so clear. So stay tuned on that one.
And that's our last
All right.
question.
I want us to thank Jim again for a really great lecture. The
Thank you.
future is bright.
Yes, thank you very much. Thank you very much. I enjoyed it.